I will talk about introduction. Thermodynamics is the study of energy and help improve how we use solar power. By using thermodynamic principle, solar energy system can be made more efficient and reduce energy loss. Solar system work by turning sunlight into electricity using PV panels or by using heat through solar thermal system. However, there is some problem like depending on sunlight, low efficiency, high cost, heat loss, and difficulty storing energy for later use. By applying thermodynamics, we can design better system that can capture and use more solar energy, making more reliable and useful for life.
Now, let's look at how solar energy follows thermodynamic principles, specifically the first and second law of thermodynamics. The first law, or the law of the energy conservation, tells us that energy cannot be created or destroyed. It can only change form. In solar energy systems, we can clearly see this in action. For example, solar thermal collectors convert sunlight into heat energy, while photovoltaic cells convert solar radiation directly into electricity. Although some energy is lost during the process, the total amount of energy remains constant.
I will be presenting about the industrial application of solar energy, followed by an overview of the challenge faced and the solutions that are being developed to address them. To begin with, let's look at how solar energy is applied in different industrial sectors. Firstly, in the food and beverage industry, solar energy plays a key role in solar drying. This method is used to dry agricultural products such as fruits, spice, coffee bean, and tea leaf, especially in countries like India, Kenya, and Thailand. As a result, it reduces the need for wood or gas dryers, making the process more environmentally friendly. In addition, solar pasteurization is used in dairy and juice processing plants to heat fluids without the use of fossil fuels. For example, Nestle uses solar thermal system for both process heating and hot water across several of its factories worldwide. Secondly, in the textile industry, solar energy is used for water heating and dyeing. Solar thermal collectors provide the necessary hot water for washing, dyeing, and finishing fabrics. A good example can be seen in Tirupur, India, where many textile industries have adopted solar heating to reduce their dependence on diesel boilers. Next, let's look at chemical and pharmaceutical industry. Specifically, this system provides process heat, which is essential for many chemical processes that require temperature between 100 to 250 Celsius. To illustrate, a pharmaceutical company in Spain uses a parabolic solar thermal system to generate steam for chemical reaction and sterilization. Alright, so moving on. Now that we have seen the application, let's take a look at the main challenge in using solar energy and how they are being addressed. One of the major challenges is the dependence on sunlight. Solar power can only be generated when the sun is shining, so it is very depending on the time of day, weather, and season. This makes energy supply inconsistent. Other than that, another issue is storage limitation. Energy is not always produced when it's needed, so without proper storage system, a lot it can go to waste. Last but not least, we also face limits in efficiency. Solar panels have physical restrictions in how much sunlight they can convert into electricity. Most standard panels only reach about 30% efficiency due to natural thermodynamic limits. And finally, there is a matter of cost. Installing solar system for industrial can be expensive upfront, which can be a barrier for a small and medium-sized company. Fortunately, the good news is that innovative solutions are being developed to tackle this problem. To begin with, I would say that advanced energy storage systems such as lithium-ion batteries and molten salt storage, because it allows excess solar energy to be stored and used at night or during cloudy weather. Moreover, industries are turning to a hybrid system, combining solar with other sources like wind, biomass, or even backup fossil fuels. This will help to ensure that a stable and continuous energy supply. In addition, the use of advanced material is improving efficiency. For example, multi-junction solar cell and concentrated solar power system are helping to convert more sunlight into usable energy.
Next, I will talk about case analysis. One real-world example is the solar system is ECSP in the Gemma solar plant in Spain. This plant uses mirror to focus sunlight and heat molten salts, which then produce steam to electricity. Thanks to thermodynamic design, it can store heat up to 15 hours, allowing to produce electricity even at night. According to TerraSol Energy, Gemma Solar can supply power to over 27,000 homes and save around 30,000 tons of carbon dioxide emission per year. In another study, research from MIT improved the efficiency of solar panels by applying TPC system, which use heat radiation from a thermal source to generate electricity, reaching efficiency over 14% compared to the typical 15 to 20% of standard PV panels. This case shows how thermodynamics help boost solar energy system by increasing efficiency, improving energy storage, and enabling round-the-clock power generation.
So, let's talk about the solutions and technological advancements. High efficiency solar panels. Solar panels these days are getting way better. With monocrystalline and multi-junction cells, they can produce more electricity using the same amount of sunlight. So, you get more power even when space is limited. Solar tracking system. Ever seen a solar panel that moves with the sun? That's a tracking system. It follows the sun across the sky, which helps the panels collect more energy throughout the entire day, not just when the sun is directly above. Energy storage improvement. Of course, solar energy is useless without good storage. That's where newer lithium-ion and solid-state batteries come in. They are safer, last longer, and can store more energy, perfect for cloudy days or nighttime. Smart inverter technology. Smart inverters are like the brains of the system. They don't just convert energy, they also keep an eye on performance, help improve efficiency, and let you know if something's not working right. Bifacial panels. And then there's bifacial panels, or also known as the two-sided panel. These cool panels can absorb sunlight from both the front and the back, so even reflected light gets turned into electricity. Pretty smart, right?
In conclusion, the application of thermodynamic principles to solar energy systems plays a vital role in enhancing energy efficiency and sustainability. By understanding and utilizing the first and second laws of thermodynamics, we can improve the conversion of solar energy into usable power with minimal resources. Real-world examples show that industries are already benefiting from thermodynamics optimization, such as improved heat exchangers and advanced photovoltaic designs. However, challenges like energy storage and intermittency still remain. Therefore, continuous innovation, technological advancement, and research are essential to maximize the potential of solar energy as a clean, reliable, and long-term energy solution for the future.